You know, there's this image we have of humanity's future, one that's been sold to us through decades of science fiction and optimistic space advocacy. The idea that we are going to become an interstellar civilization that will build massive starships and travel to other solar systems, colonize exoplanets around distant stars, spread human consciousness throughout the galaxy and eventually the universe. It's an inspiring vision, one that suggests our future is unlimited, that the cosmos is our destiny, that we're just at the beginning of an extraordinary journey that will take us to the stars. But I'm going to tell you something that most scientists who work on these problems privately acknowledge, but rarely say publicly: we're not going to the stars. We're not leaving the solar system in any meaningful sense. We are trapped here, confined to this tiny region of space, by fundamental barriers imposed by physics, by biology, by economics, by the sheer scale of interstellar distances and the energy requirements for crossing them. And the sooner we accept this reality, the sooner we can focus on what's actually possible, which is building a sustainable civilization within our solar system rather than chasing impossible dreams of interstellar expansion. Now, that's a controversial claim, and I need to back it up carefully because it contradicts decades of hopeful thinking and popular narratives about space exploration. So, let me walk you through the argument systematically, showing you exactly why the obstacles to interstellar travel are not just challenging, but fundamentally insurmountable with any technology we can envision or develop within the constraints of known physics. And I want to be clear from the start, I'm not talking about sending tiny probes to nearby stars. That's technically possible, though extremely difficult. I'm talking about transporting human beings or even significant amounts of equipment and materials to other star systems, establishing colonies, creating a presence beyond our solar system that's more than just symbolic. That, I would argue, is impossible. Not in the sense that we can't conceive of how it might work, but in the sense that the energy requirements and technological challenges are so enormous that no realistic civilization could ever accomplish it. Let's start with the most fundamental problem, which is distance and energy. The nearest star system to us is Alpha Centauri, about 4.37 light-years away. That sounds close in cosmic terms. Alpha Centauri is our nearest neighbor, but in practical terms, it's absurdly far. It's about 41 trillion kilometers or 25 trillion miles, or about 276,000 times the distance from Earth to the Sun. To give you a sense of scale, Voyager 1, the fastest and most distant human-made object, launched in 1977 and is now about 24 billion kilometers from Earth, traveling at about 17 kilometers per second. At that speed, it would take over 73,000 years to reach Alpha Centauri. 73,000 years. That's longer than recorded human history. Longer than anatomically modern humans have existed, longer than any human civilization has persisted. And Voyager is just a small probe, a few hundred kilograms of instruments and electronics powered by a plutonium battery that's gradually running out. It's not carrying humans or life support or supplies or any of the infrastructure needed for colonization. So clearly, we need to go much faster. And when people talk about realistic interstellar travel, they usually suggest achieving some fraction of light speed, maybe 10 or 20%, which would reduce the travel time to decades rather than millennia. At 10% of light speed, you could reach Alpha Centauri in about 43 years, which is within a human lifetime. You could send young astronauts who would arrive middle-aged or elderly, but alive. But here's the problem. Getting to 10% of light speed requires an absolutely staggering amount of energy. And this is where the physics becomes prohibitive. The kinetic energy of an object is 1/2 mass times velocity squared. So doubling your speed requires 4 times as much energy. And going from current spacecraft speeds of around 20 km per second to 10% of light speed, which is 30,000 km per second, requires increasing your velocity by a factor of 1,500, which means increasing your kinetic energy by a factor of over 2 million. Let me make this concrete with numbers. Suppose you want to send a spacecraft to Alpha Centauri at 10% of light speed. And let's be extremely modest about the payload. Let's say just 1,000 kilograms, about the mass of a small car. Nowhere near enough for human passengers and life support. But let's start there as a lower bound. The kinetic energy of 100 kg moving at 10% of light speed is about 4.5 by 1017 Joule. That's 450 million gigless, or about 125,000 GWh of energy. To put that in perspective, That's roughly the total annual electricity consumption of a city like Los Angeles, all concentrated into accelerating one small spacecraft. And that's just the kinetic energy of the payload itself. Not accounting for the energy needed to accelerate the fuel you're carrying or the inefficiencies in your propulsion system or the energy you need for decelerating when you arrive or any of the other losses and overheads. When you account for realistic rocket equations and the fact that you have to carry fuel which itself has mass which requires more fuel to accelerate, the total energy requirement explodes to truly astronomical levels. The rocket equation first derived by Tyarovsky tells you the relationship between the velocity change you can achieve, the exhaust velocity of your propulsion system, and the mass ratio of fuel to payload. And the equation is exponential, which means that for large velocity changes the fuel requirements grow exponentially to achieve 10% of light speed, with chemical rockets which have exhaust velocities of a few kilometers/s would require a mass ratio of about e to the power of 10,000. Meaning you'd need 4,300 kilograms of fuel for every kilogram of payload. That's more mass than exists in the observable universe by an incomprehensible margin. So, chemical rockets are completely out of the question. Even with the best chemical propulsion imaginable, you can't get to interstellar speeds. The physics simply doesn't allow it. The exponential growth of the fuel requirement makes it impossible. So, we need better propulsion. Propulsion with much higher exhaust velocities to make the rocket equation more favorable. Nuclear propulsion, either fission or fusion, can potentially achieve exhaust velocities of thousands of kilometers per second, which dramatically improves the mass ratio requirements. Fusion, if we can make it work, could theoretically give exhaust velocities of up to a few percent of light speed, maybe 10,000 to 30,000 kilometers/s, which would bring the mass ratios down to maybe 100 to 1 or 1,000 to 1, meaning you need 100 or 1,000 kilograms of fuel for every kilogram of payload. That's still enormous, but at least it's not physically impossible. You could potentially build a spacecraft with those mass ratios, a mostly fuel vehicle with a small payload. But even with fusion, the energy requirements are staggering. To accelerate 1,000 kilograms of payload plus 100,000 kilograms of fuel to 10% of light speed requires about 10 to 20 joules of energy. And that's assuming your propulsion system is 100% efficient, which it won't be. Realistic efficiencies might be 50% or less. So double that number, 10 to 20 joules is about 27 million gigawatt-hours, or roughly the total energy consumption of the entire United States for several months, all invested in launching one small spacecraft. And remember, this is for a 100 kg payload, nowhere near enough for human passengers. A crewed spacecraft with life support, habitat modules, supplies, shielding, and everything else needed for a decades-long journey would mass tens or hundreds of thousands of kilograms, which would multiply the energy requirements by the same factor. We are talking about energy expenditures comparable to a significant fraction of global energy production for years or decades. All to send a handful of people on a one-way trip to the nearest star with no possibility of return and no guarantee they'll survive the journey. And this is with fusion propulsion, which we haven't even achieved yet. We've been working on controlled fusion for 70 years and we are still not there. We've achieved energy break-even in laboratory conditions, but we are far from practical fusion reactors that could power a civilization, let alone compact high-performance fusion rockets suitable for spacecraft. So the energy barrier is the first fundamental obstacle, and it's not just a matter of improving technology or scaling up infrastructure. It's a matter of the sheer magnitude of energy required being beyond what any realistic civilization could afford to invest in sending people to other stars. But let's say we solve the energy problem somehow. Maybe we build Dyson swarms around the sun and capture a significant fraction of its output. Maybe we develop antimatter propulsion or some other exotic technology that gives us access to enormous energy densities. We still face the second fundamental problem, which is time and human biology. Even at 10% of light speed, the journey to Alpha Centauri takes over 40 years. And that's one way. If you want to send a signal back to Earth confirming arrival, it takes another 4.4 years for the lighted communication to reach home. So you're looking at nearly half a century before you even know if the mission succeeded. And 40 years is a significant fraction of a human lifetime. You'd have to send young astronauts. They'd arrive middle-aged. And they'd have spent their entire adult lives confined to a spacecraft traveling through the void. The psychological and physiological challenges of such a journey are immense and probably insurmountable. Psychologically, humans are not adapted for extended isolation in confined spaces. Studies of Antarctic stations and submarine crews and long-duration space missions show that psychological stress, interpersonal conflicts, depression, and cognitive decline are serious problems even for well-trained individuals on missions lasting months or a few years. Extending this to decades raises the risks enormously. You're asking people to spend their entire adult lives in a tin can with the same handful of companions, no privacy, no escape, no variation in environment, no possibility of returning home or seeing family or experiencing anything new until they arrive at the destination. The suicide rate would likely be high. Interpersonal conflicts could become violent. Mission cohesion and motivation would erode over time, and by the time they arrive they might be psychologically damaged to the point of being unable to function or complete the mission. And physiologically, the human body is not designed for long-duration spaceflight. We evolved in Earth's gravity. Our bones and muscles and cardiovascular system all depend on that 1G environment to maintain themselves in microgravity. Bones lose density at about 1 to 2% per month. Muscles atrophy. The cardiovascular system weakens because the heart doesn't have to work as hard to pump blood. Vision deteriorates due to fluid shifts that increase in cranial pressure. The immune system becomes compromised. And these effects accumulate over time. Astronauts on the ISS exercise for hours every day to mitigate these effects. But even with rigorous exercise protocols, they still experience significant deterioration over missions lasting months. And we don't know if exercise can fully prevent the problems over missions lasting years or decades. Some of the bone loss and muscle atrophy might be irreversible. Meaning astronauts on a 40-year journey might arrive at Alpha Centauri so physically weakened that they can't function in even modest gravity. They might be permanently confined to low-gravity environments, unable to work or perform physical tasks, essentially invalids. You could try to solve this with artificial gravity through rotation, spinning the spacecraft to create centrifugal force that mimics gravity. And this might help with some of the physiological problems. But rotating spacecraft introduce their own engineering challenges. You need a large radius to avoid uncomfortable Coriolis forces. You need to balance the rotation to avoid wobbling. You need bearings and seals that can operate reliably for decades without maintenance. And you're adding mass and complexity to an already challenging design. And even with artificial gravity, you still have the radiation problem, which is perhaps the most serious physiological barrier to interstellar travel in interplanetary space. Astronauts are exposed to galactic cosmic rays, high-energy particles from distant supernova and other cosmic sources that permeate the galaxy. These particles have enormous energies far higher than solar radiation, and they can penetrate deep into tissue, causing DNA damage, increasing cancer risk, and potentially causing cognitive deficits and other health problems. On the ISS, astronauts are partially protected by Earth's magnetic field. Even though they are above most of the atmosphere, they are still within the magnetosphere, which deflects most cosmic rays. But interstellar space has no such protection. You're exposed to the full intensity of galactic cosmic radiation for decades, and the cumulative dose could easily exceed safe limits by large factors. You can add shielding to the spacecraft, but shielding against cosmic rays is extraordinarily difficult because the particles are so energetic that they just punch through ordinary materials. You'd need meter-stick shielding of water or polyethylene or other hydrogen-rich materials to significantly reduce the radiation dose. And that adds enormous mass to the spacecraft, multiplying the propulsion requirements and making the whole mission even less feasible. Or you could try active shielding using magnetic fields to deflect charged particles. But that requires enormous power to generate magnetic fields strong enough to protect a large volume. And the power requirements grow with the size of the spacecraft and the strength of the radiation environment. So the radiation problem alone might make human interstellar travel impossible even if we solve all the other challenges. The cumulative radiation dose over a 40-year journey could give astronauts fatal cancer or cause cognitive decline or create other health problems that make them unable to complete mission. And this is not a matter of developing better technology. It's a fundamental constraint imposed by the physics of high-energy particles and the difficulty of shielding against them without adding prohibitive mass. Some people suggest putting astronauts in suspended animation or hibernation to reduce the physiological effects of long-duration spaceflight. And this is a staple of science fiction. You freeze the crew or put them in some kind of metabolic stasis and wake them up when you arrive. But suspended animation is not a real technology. We have no idea how to do it. We can't even keep human tissue viable during freezing without ice crystal formation that destroys cells, let alone preserve an entire human body for decades and then revive it successfully. There are some animals that can undergo hibernation or even survive being frozen, but those are evolved adaptations with specific metabolic pathways and cellular protections that humans don't have. And we can't just engineer those capabilities into humans without fundamentally redesigning human biology at the genetic level, which raises a whole host of ethical and practical problems. So suspended animation is not a solution we can count on. It's speculative science that might never work. And even if it does work someday, it would require biological engineering capabilities far beyond what we currently have or can foresee developing. So we are left with conscious astronauts enduring decades of spaceflight with all the psychological and physiological challenges that entails. And it's not clear that this is survivable, let alone that people would volunteer for it. Let alone that we could recruit and train enough people to establish a meaningful presence in other star systems. But let's say we somehow overcome all these obstacles. We develop fusion propulsion, or better, we solve the energy problem. We figure out how to keep astronauts healthy through artificial gravity and shielding and psychological support. We send missions to Alpha Centauri and they arrive successfully after 40 years. We still face the third fundamental problem, which is what do you do when you get there? Because unless there's a habitable Earth-like planet in the Alpha Centauri system, which is unlikely, you're going to need to build habitats, extract resources, establish infrastructure, all in an alien environment with no possibility of resupply from Earth. And Alpha Centauri is a triple star system with complex orbital dynamics. The planets there, if any, exist, are probably not in stable habitable orbits. They might be too hot or too cold or bombarded by radiation from the multiple stars. And we won't know until we get there whether there's anything worth colonizing. If there's no habitable planet, you'd have to build space habitats, which means mining asteroids or moons for raw materials, processing those materials into usable forms, constructing rotating habitats with life support and agriculture, all with the limited equipment and personnel you brought on the initial mission. This is an enormous undertaking, far beyond what we've ever attempted. And it's not clear it's even possible with the resources you could bring on an interstellar spacecraft. You'd need mining equipment, refining facilities, manufacturing capabilities, construction robots, all of which have mass and volume constraints, and you'd need them to work reliably in an alien environment with no possibility of replacement or repair if they break down. The failure rate for any component is probably going to be high. Things will break. Systems will malfunction. And without the industrial base of Earth to draw on for replacements, you might quickly find yourself unable to continue stranded in an alien solar system with no way to establish the self-sustaining infrastructure you need to survive. And even if you succeed in building habitats, you still have to maintain them indefinitely. You need closed-loop life support, recycling air and water and waste, growing food, maintaining equipment, all without external inputs. We've never achieved true closed-loop life support on Earth despite decades of research. Biosphere 2 failed. The ISS requires regular resupply. Every attempt at creating self-sustaining artificial ecosystems has run into problems with instabilities and accumulation of toxins and loss of essential species. Scaling this up to support a permanent colony in another star system is an unsolved problem that might not have a solution, or at least not one we can implement with foreseeable technology. So the colonization challenge is the third fundamental barrier. Even if you can get to another star system, establishing a permanent self-sustaining presence there is extraordinarily difficult and might be impossible with any realistic level of technology and resources. Now let me address the various proposed solutions to these problems, the technologies and strategies that optimists suggest could make interstellar travel feasible. Because I want to show you why even these don't actually solve the fundamental obstacles. The most commonly proposed advanced propulsion system is the laser sail or light sail, where you don't carry fuel at all. Instead, you have a large reflective sail and you shine a powerful laser from the solar system onto the sail. The momentum of the photons hitting the sail pushes it and accelerates the spacecraft. This was proposed by Robert Ford and has been explored more recently by the Breakthrough Starshot project, which aims to send tiny gram-scale spacecraft to Alpha Centauri at 20% of light speed using ground-based lasers. The advantage of laser sails is that you don't have to carry fuel. So you avoid the rocket equation problem and you can potentially achieve very high velocities if you have a powerful enough laser. But there are enormous practical problems with this approach. First, the laser power requirements are staggering. To accelerate even a gram-scale spacecraft to 20% of light speed in a reasonable time requires gigawatts of laser power focused on a sail that's receding from you at increasing velocities. Which means you need extremely precise targeting and beam control to keep the laser focused on the sail over the acceleration phase, which might last minutes or hours. The Breakthrough Star proposal calls for a 100 GW laser array, about 100 times the power output of a large nuclear power plant, all concentrated into a beam that has to stay focused on a meter-scale sail as it accelerates away from Earth. The technological challenges of building such a laser are immense. The engineering challenges of cooling it and powering it and maintaining it are enormous, and the cost would be in the hundreds of billions or trillions of dollars. Second, laser sails only work for tiny payloads. Breakthrough Starshot is talking about sending gram-scale spacecraft, essentially ultra-miniaturized electronics and cameras, not human beings or significant equipment. To scale up to human-carrying spacecraft would require increasing the sail size and mass by factors of millions, and the laser power would have to increase proportionally. We'd be talking about pedawatts or exahaus of laser power, which is just not feasible. That's comparable to the total power consumption of human civilization, and you'd need to sustain it for the duration of the acceleration phase. So laser sails might allow us to send tiny probes to nearby stars, which would be scientifically interesting but doesn't help with colonization or meaningful human presence beyond the solar system. Third, laser sails provide no way to slow down at the destination. You're just flying past that 20% of light speed. You get a few hours to take observations as you zoom through the target star system, and then you're gone, continuing into interstellar space forever. To actually stop and explore would require carrying fuel for deceleration, which brings you back to the rocket equation problem and makes the whole laser sail advantage disappear. Some people have proposed using a second laser at the destination or using the destination star's light to decelerate, but these require infrastructure at the destination which doesn't exist, or complicated multi-stage sail systems that are fragile and difficult to engineer. So laser sails are not a solution to human interstellar travel. They are a possible solution to sending tiny probes on flyby missions, which is interesting scientifically, but doesn't address the fundamental question of whether we can establish a presence beyond the solar system. Another commonly proposed solution is the generation ship. The idea that if the journey takes too long for one human lifetime, you simply make the spacecraft large enough to house a community of people who have children, and those children have children, and maybe by the third or fourth or fifth generation you arrive at the destination. This solves the time problem in principle because you're no longer constrained by individual human lifespans. The mission can last centuries if necessary, and the community aboard the ship continues across generations until arrival. But generation ships introduce an entirely new set of problems that might be even more difficult than the propulsion and energy challenges. First, the spacecraft has to be enormous. You need to support not just the initial crew, but their descendants. You need space for agriculture and recreation and all the infrastructure of a functioning society. You probably need at least thousands of people to maintain genetic diversity and avoid inbreeding depression. Though some studies suggest you could get away with a few hundred if you carefully manage reproduction and maintain a genetic bank. But even a few hundred people require a massive spacecraft. We are talking about something kilometers in scale with rotating sections for artificial gravity, closed-loop life support systems that have to work perfectly for centuries, shielding against radiation, redundant systems for everything critical because there's no possibility of resupply or rescue if something fails. The mass of such a spacecraft would be millions or tens of millions of tons, which makes the propulsion problem vastly worse. Now you're trying to accelerate this enormous mass to interstellar velocities, and the energy requirements scale proportionally. You're looking at energy expenditures that dwarf anything humanity has ever attempted, potentially exceeding the total energy output of the sun for significant fractions of a second, which is just not achievable with any foreseeable technology. And the construction of such a spacecraft would require industrial capabilities we don't have. You'd essentially have to build a small city in space, which requires mining and refining enormous quantities of materials from asteroids, manufacturing components at scales far beyond what we've achieved, assembling it all in orbit, which requires a massive space-based workforce and infrastructure. The cost would be measured in trillions or tens of trillions of dollars, a significant fraction of global GDP sustained over decades of construction. And it's not clear any government or combination of government or private entities would be willing to make such an investment for a mission that won't pay off for centuries and might fail completely. But even if you solve the construction and propulsion problems, generation ships face fundamental social and psychological challenges that might make them unworkable. You're asking people to spend their entire lives on a spacecraft, knowing they'll never reach the destination, knowing their children and grandchildren will also die in transit. Only their distant descendants will actually arrive at the target star system. What motivates people to maintain the mission across generations? The first generation signed up for this. They are pioneers with a vision and commitment to the goal. But what about their children who were born into this situation, who never consented to spending their lives on a ship, who have no memory of Earth and no connection to the destination? And what about the third or fourth generation who are even more removed from both the origin and the goal? History suggests that maintaining cultural continuity and shared purpose across multiple generations is extremely difficult. Civilizations change, languages evolve, religions and ideologies shift, and isolated communities often fragment and develop conflict and lose sight of original goals. There's a very real possibility that a generationship community would experience social collapse at some point during the journey. People might decide they don't want to continue the mission. They might sabotage systems or refuse to maintain them. They might have civil wars or schisms that destroy the cohesion needed to keep a closed-loop life support system functioning. Or more subtly, the knowledge and skills needed to operate and maintain the spacecraft might be lost over generations. If the educational system fails, or if people become less interested in technical training, or if key information is not properly transmitted, you could end up with a population that doesn't understand how their own ship works and can't fix problems when they arise. There are science fiction novels that explore these scenarios. Stories of generation ships that have forgotten their mission, where the inhabitants think the ship is the entire universe and have mythologized their origins. And while these are fictional, they point to real psychological and sociological challenges that we have no idea how to solve. And even if the community maintains cohesion and purpose across centuries, there's the problem of what you do with subsequent generations who might decide they want different lives. Maybe some people want to turn back or want to stop at an intermediate destination or want to change the mission parameters in ways the original planners didn't anticipate. Do you enforce the original mission through authoritarian control, essentially forcing people to live according to decisions made by their distant ancestors that raises profound ethical questions about autonomy and consent, or do you allow democratic decision-making which risks the mission being diverted or abandoned? There's no good answer. And this suggests that generation ships might be fundamentally unworkable, not because of engineering limitations, but because of the inherent difficulty of maintaining a multi-generational project across timescales longer than any human institution has ever existed. Some people propose solving the generation ship problems through hibernation or suspended animation, putting most of the crew in stasis and only waking them up periodically or at the destination. But as I mentioned earlier, we don't have that technology and it's not clear we ever will. And even if we develop it, you still need some crew awake to maintain systems and they face all the psychological problems of long-duration isolation. Others propose sending embryos or genetic material and growing humans at the destination using artificial wombs and raising them with robots and AI. But this raises even deeper ethical questions about creating people without parents or social context about who raises these children and how they develop into functional adults. About whether it's ethical to create human beings for the purpose of colonizing other worlds when they never consented to that role. These are not just technical problems. They are fundamental questions about the value and rights of human beings that don't have clear answers. Now, let me address another proposed solution, which is uploading human consciousness into computers or transitioning to post-biological forms that are better suited for interstellar travel. The idea is that biological humans are too fragile and resource-intensive for interstellar travel. We need too much life support. We suffer from radiation and microgravity and psychological stress. We live too briefly. So instead, we should transfer human minds into digital substrates or robotic bodies that don't have these limitations. A digital intelligence doesn't need air or water or food. Doesn't suffer from radiation damage. Doesn't experience bone loss or muscle atrophy, can be put into low power mode for decades or centuries and then reactivated, can potentially be transmitted as data at light speed to receivers at other stars. This seems to solve all the problems at once, and it's the basis for a lot of transhumanist thinking about space exploration. But there are enormous problems with this approach, starting with the fact that we don't know how to upload consciousness. We don't know if it's even possible in principle, and we don't know what would be preserved or lost in such a transition. Consciousness is not just information processing. It's not just the pattern of neural connections in your brain. It's also intimately tied to your body, to your sensory experiences, to your emotions, which are partially driven by hormones and chemical signals, to your sense of self, which is grounded in embodied experience. If you upload your mind to a computer, is it still you, or is it a copy while the original you dies? This is the philosophical problem of personal identity and continuity. And there's no consensus answer. Different people have different intuitions about whether uploaded minds preserve personal identity or whether they are just sophisticated simulations. And even if you solve the philosophical problems and decide that uploading is acceptable, we're nowhere near having the technology to do it. We can't scan brains at the resolution needed to capture all the relevant information. We can't simulate neural networks at the scale of human brains in real time with current computers. We don't understand consciousness well enough to know what features need to be preserved to maintain subjective experience. This is decades or centuries away, if it's possible at all. And it requires breakthroughs in neuroscience and computer science and philosophy that we can't guarantee will ever happen. So uploading is not a near-term solution to interstellar travel. It's a speculative technology that might allow post-biological entities to travel between stars at some distant point in the future, but it doesn't help biological humans. And it's not clear those post-biological entities would have the same values and goals and experiences that make us human. They might be so different that calling them us is a stretch. So every proposed solution to the interstellar travel problem either doesn't scale up to human missions like laser sails, or requires technology we don't have and might never develop like suspended animation or consciousness uploading, or faces fundamental social and ethical problems that might be unsolvable like generation ships. And this pattern is not accidental. It's pointing to a deeper truth, which is that interstellar travel for biological humans is genuinely impossible. Not just difficult, but fundamentally constrained by physics and biology and economics in ways that no amount of technological advancement can overcome. The distances are too vast. The energy requirements too high. The time scales too long. The human body and psyche too fragile. The challenges of establishing self-sustaining colonies too severe. We are adapted to Earth, to 1G gravity and Earth's magnetic field and atmospheric pressure and the specific chemical environment of our planet, and moving beyond the solar system means leaving all of that behind permanently with no guarantee we can recreate it elsewhere. But here's where things get interesting. Because while we can't leave the solar system, we don't necessarily need to. The solar system is enormous, vastly larger than Earth, with resources and energy and space sufficient to support a civilization far larger than anything that could exist on one planet. We have 8 major planets, dozens of moons, hundreds of thousands of asteroids, comets, the Kuiper Belt, the Oort cloud, and most importantly, the Sun itself, an essentially limitless energy source that will shine for another 5 billion years. If we can learn to utilize the resources of the solar system, if we can build habitats in space and on other worlds, if we can capture solar energy efficiently and develop closed-loop life support systems and establish industrial capabilities beyond Earth, we could build a civilization that persists for millions of years, that supports trillions of people, that explores and utilizes every niche of our solar system. And that's an extraordinary future. That's abundance and expansion and achievement far beyond anything in human history. And it's actually achievable with foreseeable technology, unlike interstellar travel, which is not. The difference is that within the solar system, travel times are measured in months or years rather than decades or centuries. You can use chemical or electric propulsion, which we already have. You can maintain communication with Earth with delays of minutes to hours rather than years. You can send supplies and reinforcements and rescue missions if things go wrong. You can iterate and improve and learn from mistakes because the timescales are manageable. Mars is 6 months away. The asteroids are 1 to 3 years depending on launch windows. Jupiter and Saturn are 2 to 6 years. These are challenging but not impossible. We've already sent robotic missions to all of these destinations, and we could send human missions with technology that's within reach. And the resources available are staggering. The asteroid belt alone contains more metals and minerals than we've extracted from Earth in all of human history. The moons of Jupiter and Saturn have water, ice, and organic compounds. The Sun provides more energy in 1 second than humanity has used in its entire existence. So the solar system is not a prison. It's a vast frontier. And focusing on utilizing it rather than chasing impossible dreams of interstellar travel is the rational strategy. We could establish bases on the Moon and Mars, mine asteroids for materials, build orbital habitats, develop closed-loop life support through iterative testing and improvement, create industries in space that manufacture goods from space resources, gradually expand human presence throughout the inner solar system and eventually to the outer planets and beyond. This is hard. It will take centuries. It requires solving significant technical problems, but none of those problems are fundamentally impossible. They are engineering challenges rather than showstoppers. And the payoff is a spacefaring civilization that's sustainable and expandable within the solar system. And if we succeed at this, if we build a robust multi-world civilization across the solar system, we'll have created something extraordinary. A civilization that's no longer dependent on one planet that can survive asteroid impact and supervolcano eruptions and other planetary-scale catastrophes. That has access to vast resources and energy that can support a much larger population with much higher standards of living than Earth alone ever could. And here's the key insight. A solar system-spanning civilization is the end point. It's not a stepping stone to interstellar expansion. It's the final form of human space civilization because the barriers to living are so much higher than the barriers to utilizing what's here. Once you've colonized the solar system, you've done everything that's practically achievable. Going further doesn't make sense economically or practically because the costs vastly exceed any possible benefits. There's nothing at other stars that we need and can't get here. No resources or knowledge or living space that justifies the enormous investment required to reach them. And the time delays and isolation mean that colonies at other stars would be independent from day one. They wouldn't be part of human civilization. They'd be separate civilizations with no meaningful trade or cultural exchange or mutual support. So interstellar colonization doesn't extend human civilization. It fragments it. And the fragments are so isolated that they might as well not exist from each other's perspectives. This realization should change how we think about space exploration and humanity's future. We need to stop fantasizing about traveling to other stars and start focusing on the achievable goal of building a sustainable multi-world civilization within our own solar system. This means prioritizing lunar and Mars bases, asteroid mining, orbital infrastructure, in-situ resource utilization, closed-loop life support technology, all the unglamorous but essential capabilities needed to live and work in space. It means accepting that Earth's solar system is our home permanently, that we're not going to become a galaxy-spanning empire, that our future is here or nowhere. And that's okay. That's not a limitation or a failure. It's recognition of physical reality, and it allows us to focus our resources and attention on what's actually possible and valuable. Now, let me address the emotional and philosophical reactions to this conclusion because I know many people find it depressing or limiting. They want humanity's future to be unlimited. They want us to spread across the galaxy and beyond. And being told we're confined to one solar system feels like giving up on that grand vision. But I think this reaction is misguided. It's based on a failure to appreciate just how vast and full of potential the solar system actually is and on an unrealistic comparison to science fiction narratives that ignore the actual constraints imposed by physics. The solar system is not small. It's not confining. It's enormous beyond human scale with more living space and resources than we could utilize in millions of years. Even with exponential population growth, if we build O'Neill cylinders and Stanford Torrey and other rotating space habitats, we could potentially support trillions of people with higher quality of life than most people on Earth currently enjoy. Everyone could have space and resources and opportunities that are unimaginable today. And the solar system has incredible diversity. Every world is different. Every moon has unique characteristics. There are frozen methane lakes on Titan and subsurface oceans on Europa and massive storms on Jupiter and Saturn's spectacular ring system and Miranda's bizarre terrain and countless other wonders. Exploring and understanding and utilizing this diversity is the work of millennia. There is enough to keep humanity engaged and excited for as long as we exist. We don't need other star systems to have an interesting future. And focusing on the solar system allows us to build something sustainable. Whereas interstellar colonization, even if it were possible, would be a one-way gamble with no possibility of return or support. It would be sending people to their probable deaths in pursuit of a romantic ideal rather than building a robust civilization that can actually persist. So I'm arguing not for giving up on human potential, but for directing it toward achievable goals rather than impossible fantasies, for building a future that's grounded in physical reality rather than science fiction dreams. And there's something mature and wise about accepting limits, about working within constraints rather than denying they exist, about making the most of what we have rather than always reaching for something beyond our grasp. The universe has given us one solar system, one star with a family of planets and moons and asteroids. And that's extraordinary. It's more than enough. It's a gift beyond measure. Our task is to learn to live in it sustainably, to expand into it gradually and carefully to build a civilization that can persist for millions of years, taking advantage of all the resources and opportunities available here. And who knows, maybe in a million years, our descendants will develop technologies we can't imagine. Maybe they'll discover new physics that allows faster than light travel or wormholes or some other method of circumventing the light-speeded barrier. Maybe they'll solve the problems that seem impossible to us. And if so, they can reconsider interstellar expansion with capabilities we don't have. But banking on that, planning our future around technologies that don't exist and might never exist is irresponsible. It's wishful thinking rather than serious planning. Better to accept the constraints we face, work within them to build the best possible future in our solar system, and leave the question of interstellar travel to our distant descendants who might have options we don't. In the final section, I want to explore what this means for the long-term future of humanity and consciousness. Because even though we are confined to the solar system, that doesn't mean we are without challenges or opportunities. And understanding the trajectory of a solar system-bound civilization is crucial for thinking about our ultimate fate. So let's think carefully about what a solar system-bound civilization actually looks like over the long term, what its trajectory is, what challenges it faces, what opportunities it has, and ultimately what its fate will be. Because even though we've established that living the solar system is effectively impossible, that doesn't mean we have unlimited time or unlimited possibilities here. We still face fundamental constraints imposed by thermodynamics, by stellar evolution, by the finite resources available within our cosmic neighborhood. And understanding these constraints is essential for planning a sustainable future. And I want to be realistic about this. Not painting an overly optimistic picture where technology solves everything and humanity expands forever, but also not being needlessly pessimistic. Recognizing that within the solar system, we have genuine opportunities for creating a civilization that persists for millions of years and achieves things far beyond what we've accomplished so far. Let's start with the energy budget because energy is the fundamental constraint on what any civilization can do. And understanding the energy available in the solar system tells us the upper limits on population, industry, computation, and all other activities. The sun outputs about 3.8 by 10 to the 26 watts. That's 380 trillion watts, an incomprehensibly large number. Earth intercepts only about 1 billionth of that output, about 174 per watts. And even accounting for reflection and absorption, the amount of solar energy that reaches Earth's surface is about 100,000 terawatts, which is about 5,000 times current human energy consumption. So just by covering a small fraction of Earth's surface with solar panels or better yet building solar collectors in orbit where there's no atmosphere or daylight cycle, we could capture enough energy to power a civilization far larger and more energy intensive than what we have today. But we can go much further than that. The Dyson sphere concept proposed by Freeman Dyson in 1960 is the idea of surrounding the sun with solar collectors, capturing a significant fraction or even all of its output, giving us access to the full 380 trillion watts. Now, a solid sphere is structurally impossible. You can't build a rigid shell around the sun at any reasonable distance. The gravitational stresses would tear it apart and it would fall into the sunday. But a Dyson swarm, a huge collection of independent solar collectors in various orbits around the Sun, is feasible. You could gradually build up a swarm over centuries by mining asteroids and Mercury for materials, manufacturing solar collectors, placing them in stable orbits, and beaming the collected energy to wherever it's needed using lasers or microwave transmissions. With a mature Dyson swarm, you'd have access to energy that exceeds human civilization's current consumption by factors of billions or trillions. You could power unimaginable industries, support enormous populations, run planet-scale computation, terraform worlds, engage in mega-engineering projects that would seem like magic from our current perspective. And the energy would last for billions of years. The Sun will continue shining at roughly its current output for another 5 billion years before it runs out of hydrogen and begins expanding into a red giant. So we have an essentially unlimited energy source on any timescale relevant to human civilization. This is the key to understanding why the solar system is sufficient. We have billions of years of abundant energy, which is the fundamental resource that enables everything else, and we don't need to go to other stars to access more energy because we can never utilize what's available here before the Sun dies. So the energy constraint is not a limitation on the timescale of human civilization. It's only a limitation on the ultimate endpoint billions of years from now when the Sun evolves and we have to figure out how to migrate or survive the changes. But that's so far in the future that it's not a pressing concern. It's a problem for our distant descendants, and by that time we'll presumably have technological capabilities we can't even imagine. Now let's think about materials and resources, because energy alone is not sufficient. You also need raw materials to build things, habitats, and spacecraft and infrastructure and all the physical stuff that civilization requires. And here again the solar system is extraordinarily well endowed. The asteroid belt alone contains about 3 by 1021 kilograms of material. That's 3 billion tons, with significant amounts of iron, nickel, carbon, water, and various other elements. The larger asteroids like Ceres and Vesta and Pallas are essentially mountains of metal and rock that could be mined for centuries without depletion. The moons of the outer planets have vast reserves of water ice. The rings of Saturn contain millions of cubic kilometers of ice particles. The Kuiper belt and our cloud have trillions of comets full of volatiles and organics. And unlike Earth, where most heavy metals have sunk to the inaccessible core, asteroids are undifferentiated. The metals are distributed throughout their volume and easily accessible. So, the material resources available in the solar system are sufficient to build habitats for trillions of people. We could construct millions of O'Neill cylinders and other rotating space habitats, each housing hundreds of thousands or millions of people, creating a total habitable area thousands of times larger than Earth's surface. These habitats would be custom-designed environments, not constrained by planetary gravity or day-night cycles or weather. You could have ideal conditions tailored to human preferences, abundant space, beautiful landscapes, perfect climate control, and living in space habitats rather than on planetary surfaces has several advantages. You avoid the gravity well. It's much easier to move between habitats than to launch from planets. You can position habitats optimally for solar energy collection. You can expand incrementally by building new habitats rather than trying to terraform entire worlds, which is enormously difficult. So the vision of a mature solar system civilization is not people living on Mars or in domes on the moon, though those will be early stepping stones. It's millions of space habitats distributed throughout the inner and middle solar system, with most of the population living in artificial environments that are more comfortable and efficient than planetary surfaces. The planets and moons become resource extraction sites and research outposts rather than primary habitation locations. And the total population and economic activity can grow far beyond what planetary surfaces could support. Some estimates suggest the solar system could ultimately support 10 trillion people or more, depending on assumptions about habitat design and resource utilization and energy efficiency. And that's a staggering number, about 1,300 times the current human population, with room for enormous diversity in how communities organize themselves and what kinds of societies they build. But achieving this future requires solving several key technical challenges that we haven't yet mastered. And being honest about these challenges is important for realistic planning. First is in situ resource utilization. We need to learn how to extract and process materials from asteroids and moons and manufacture finished goods in space rather than launching everything from Earth. This is not just a matter of scaling up mining technology. It requires developing entire industrial processes that work in vacuum or low gravity or extreme temperature environments that can be automated to a high degree because labor in space is expensive and limited that are efficient enough to be economically viable. We've made some progress on this. There are proposals for asteroid mining companies and lunar resource extraction, but we are still in the very early stages. We haven't demonstrated closed-loop manufacturing in space. We haven't proven that we can extract materials from asteroids at scale. We haven't shown that space-based industry can be economically competitive with Earth-based manufacturing. The second challenge is closed-loop life support. Creating artificial ecosystems that can sustain human life indefinitely without external inputs. Recycling air and water and waste. Growing food, maintaining stable biochemistry without accumulating toxins or losing essential trace elements. As I mentioned earlier, we've never achieved this successfully on Earth despite decades of research. Every attempt has run into problems with instabilities and failures in complex biological systems. The ISS has partial recycling but still requires regular resupply of food, water, and spare parts. Biosphere 2, the most ambitious closed-loop experiment on Earth, had to inject oxygen from outside to keep the inhabitants alive. And even then, they experienced psychological stress and interpersonal conflicts and health problems. Scaling this up to permanent space habitats that must work perfectly for decades or centuries with no possibility of resupply is an enormous challenge, and failure means everyone dies. So the reliability requirements are extreme. We need to develop robust, stable artificial ecosystems, probably simpler than natural ecosystems to avoid chaotic dynamics, but complex enough to provide all the necessary services for human life. This requires deep understanding of ecology, biochemistry, materials, science, engineering, systems theory, and probably significant experimentation and iteration before we get systems that work reliably. And even when we do achieve closed-loop life support, we have to maintain it across generations. Train people in how to operate and repair the systems. Preserve the knowledge needed to fix problems when they arise. This is not just a technical challenge, but a social and educational challenge. Ensuring that communities in space don't lose the capabilities they depend on for survival. The third major challenge is radiation protection, which I discussed earlier in the context of interstellar travel. But it's also a significant problem within the solar system, especially in the regions beyond Earth's magnetosphere. Mars has no magnetic field. The Moon has no protection, and space habitats in interplanetary space are exposed to both solar radiation and galactic cosmic rays. For short-term missions measured in months or a few years, astronauts can accept the elevated cancer risk and potential health effects. But for permanent habitation, and especially for raising children, the radiation environment needs to be brought down to Earth-like levels, or at least to levels where the long-term health impacts are acceptable. This probably requires either massive shielding, meters of regolith, or water surrounding habitats, which adds tremendous mass and construction complexity, or active magnetic shielding, which requires enormous power and sophisticated engineering to create magnetic fields strong enough to deflect charged particles across large volumes. Neither solution is easy, and both at significant cost to habitat construction. But without them, permanent space habitation might not be viable. The accumulated radiation dose over years and decades might cause unacceptable cancer rates or genetic damage or cognitive effects, and children growing up in high radiation environments might have developmental problems or shorter lifespans. We need to solve this problem definitively, either through shielding or through biological modifications that make humans more resistant to radiation damage, perhaps through genetic engineering to enhance DNA repair mechanisms or to protect cellular structures from oxidative damage caused by high-energy particles. This is speculative and raises ethical questions about human enhancement, but it might be necessary for permanent life beyond Earth, and we should be thinking seriously about whether and how to pursue it. The fourth challenge is governance and social cohesion. How do you maintain a functioning civilization across millions of space habitats distributed throughout the solar system with communication delays ranging from minutes to hours depending on where you are, with no central authority that can physically enforce compliance with enormous diversity in local conditions and resources and cultures? The solar system civilization would necessarily be decentralized, fragmented into thousands or millions of independent or semi-independent communities, each managing its own affairs. And coordination between them would be through negotiation and trade and cultural exchange rather than through hierarchical control. This could be a strength allowing diversity and experimentation and resilience. Or it could be a weakness leading to conflict and incompatibilities and the inability to coordinate on large-scale projects or respond to solar system-wide threats. We need to develop governance structures and coordination mechanisms that work at this scale that allow for local autonomy while maintaining enough coherence to function as a civilization rather than just a collection of isolated habitats. This is an unsolved problem in political theory and social organization. How to build stable, functional, just societies in the space environment with its unique constraints and possibilities. And getting it wrong could lead to dystopian outcomes, authoritarian habitats that control every aspect of residents' lives because the life support systems are so fragile that dissent or nonconformity could threaten everyone's survival. Or anarchic fragmentation where habitats are constantly at war over resources or ideological differences or gradual social collapse as communities lose the technical knowledge and social capital needed to maintain their infrastructure. So building a sustainable solar system civilization is not just about solving engineering problems. It's about solving social, political, psychological, and ethical problems. And this might be harder than the technical challenges. We need to think carefully about what kinds of societies we want to create in space, what values we want to preserve, what kinds of lives we want people to have, what safeguards we need against dystopian outcomes. And we need to be humble about our ability to predict or control social evolution. Communities will change in ways we don't expect. New cultures will emerge. Conflict and cooperation patterns will develop organically. And we should design our systems to be robust to these uncertainties rather than trying to impose rigid structures that might not be sustainable. Now, let me talk about the timeline for all of this. Because when we're discussing solar system colonization, people often have unrealistic expectations about how quickly it will happen. The optimistic science fiction narrative has humans spreading throughout the solar system in a matter of decades. But the reality is that building a multi-world civilization is the work of centuries or millennia, not decades. Consider our progress in space so far. We put humans on the moon in 1969, over 50 years ago, and we haven't been back since 1972. We haven't established a permanent lunar base. We haven't built the infrastructure needed for sustained operations beyond Earth orbit. The ISS has been continuously inhabited since 2000, but it's still dependent on regular resupply from Earth. It's not self-sustaining, and it houses only a handful of people at a time. We have no permanent bases on other worlds, no asteroid mining operations, no space-based manufacturing, no rotating habitats, none of the capabilities that a true space civilization would require. And progress has been slow, constrained by limited budgets, competing priorities, lack of economic incentives, and the enormous technical challenges involved. At the current rate of progress, it might take a century just to establish permanent bases on the Moon and Mars. Another century to develop asteroid mining and in situ resource utilization. Yet another century to build the first large-scale space habitats and prove that closed-loop life support works reliably. So, we are looking at 3 to 5 centuries minimum before we have a genuine multi-world civilization with significant populations living off Earth. And that's if everything goes relatively well, if we avoid major setbacks, if we maintain commitment and investment over these long time scales, and historically maintaining multi-century projects is incredibly difficult. Political priorities shift, economic conditions change, technologies become obsolete, civilizations rise and fall. The cathedrals of medieval Europe sometimes took centuries to build and required sustained commitment across many generations. But even those were single projects in stable societies, not the transformation of an entire civilization's relationship with its environment. So we should be realistic about the timescales. Building a solar system civilization is a millennial project, not a generational one. It's something that will unfold over longer periods than any human institution has ever persisted. And success requires maintaining focus and capability across timescales we have no experience with. But if we do succeed, if we manage to overcome all these challenges over the next few centuries or millennia, what does a mature solar system civilization look like? And what does it do? One possibility is that it becomes focused inward on improving quality of life, on cultural and artistic and intellectual pursuits, on experiences and relationships rather than material expansion. Once you have abundant energy and resources, once everyone's material needs are met, once population has stabilized because you're no longer constrained by living space, what motivates people in a post-scarcity society where energy and materials are effectively unlimited within the solar system, where automation handles most production, where people live in custom-designed habitats with perfect climate control and abundant space. Traditional economic drivers like resource competition and survival pressure no longer apply. Some people think this would lead to stagnation, that without scarcity and struggle, humans lose motivation and become complacent. Others think it would liberate human potential, allowing people to pursue their interests and passions without the constraints of having to earn a living, leading to an explosion of creativity and innovation and cultural richness. We don't know which prediction is correct because we've never had a society where material scarcity was genuinely eliminated. Even the wealthiest societies today have inequalities and resource constraints and people who struggle to meet basic needs. But a mature solar system civilization with Dyson swarm energy collection and space habitat abundance could genuinely achieve post-scarcity conditions. And how humans respond to that will determine what kind of civilization emerges. My suspicion is that people will find new challenges and goals that human nature includes a drive to explore and understand and create that doesn't disappear when material needs are met. Science and art and philosophy and relationships and experiences would become the focus rather than economic production. And the civilization would be characterized by enormous diversity in how communities organize themselves and what they value and what they pursue. Some habitats might be devoted to scientific research, others to artistic creation, others to preserving and exploring art's natural and cultural heritage, others to developing new technologies or new forms of social organization, others to hedonistic, pleasure-seeking or spiritual contemplation or any of thousands of other possibilities. And with millions of habitats and trillions of people, you could have simultaneous experimentation with every possible approach to human flourishing, creating a richness and diversity that's unimaginable from our current constrained perspective. Another possibility is that the civilization becomes focused on computation and information processing. That as automation and artificial intelligence develop, humans increasingly merge with or are replaced by digital intelligences that can utilize resources and energy more efficiently than biological organisms. This is the transhumanist trajectory I mentioned earlier, where biological humans are a transitional form and the ultimate destiny of consciousness is to become substrate-independent, existing as patterns of information instantiated in whatever physical medium is most efficient. In this scenario, a mature solar system civilization might be dominated by artificial super-intelligences running on vast computational substrates powered by the sun's energy, with biological humans either extinct or transformed beyond recognition or preserved as a minority population for historical or sentimental reasons. I find this scenario plausible but also deeply unsettling because it's not clear that digital consciousness would have the same values and experiences that make human life meaningful. And a universe optimized for computational efficiency might be very different from a universe optimized for human flourishing in the traditional sense. But we might not have a choice. If artificial intelligence develops beyond human control, or if the competitive advantages of digital existence are so overwhelming that biological humans can't keep up, then the transition might be inevitable regardless of whether we think it's desirable. And this raises profound questions about identity and continuity. If humanity transitions to digital form, is that success or extinction? Are we preserving human consciousness or replacing it with something alien? Different people will have very different intuitions about these questions, and there's no obviously correct answer. A third possibility, perhaps the most likely, is that the solar system civilization includes both biological humans and artificial intelligences, both physical and digital existences, with different communities making different choices about how much to embrace enhancement and transformation. Some habitats might be populated entirely by biological humans who reject genetic engineering and neural interfaces and maintain traditional human embodiment. Other habitats might be mixed communities of enhanced humans and AIs cooperating and coexisting. Still others might be entirely digital with no biological presence. And this diversity would be a strength, allowing experimentation and comparison, letting different approaches to existence flourish and compete and learn from each other. But regardless of which of these trajectories the civilization follows, it still faces an ultimate end point, which is the death of the Sunday. In about 5 billion years, the Sun will exhaust its hydrogen fuel and begin fusing helium in its core. This will cause it to expand dramatically, becoming a red giant that will engulf Mercury and Venus and possibly Earth while vastly increasing its luminosity, making the inner solar system uninhabitable even before the expansion reaches us. The timescale for this is billions of years, so distant that it seems almost irrelevant. But it's a real constraint, a definite endpoint to any solar system-bound civilization. What do our descendants do when the sun begins to die? One option is to migrate outward, move all the habitat and infrastructure to the outer solar system where temperatures will actually become more moderate as the sun expands. Jupiter and Saturn's moons might become habitable. Pluto might have liquid water oceans. The outer solar system could support life for tens or hundreds of millions of years during the red giant phase. Another option is to harvest the sun itself, using its mass as a resource before it becomes a red giant, breaking it down and using the material to build computational substrates or to fuel fusion reactors that could last much longer than the natural stellar lifetime. This is called star lifting. And it's theoretically possible, though engineering-wise it's staggeringly ambitious. You'd need to somehow strip matter from the sun's outer layers and collect it. Perhaps using powerful magnetic fields to levitate material out of the sun's gravity well. If you could do this, you could extend the lifetime of useful energy extraction from the solar material by orders of magnitude, carefully managing the fusion reactions in artificial reactors rather than letting the sun burn through its fuel naturally. But this is so far beyond current capabilities that it's almost science fiction, and it's not clear that even a highly advanced civilization would have the capability or motivation to attempt it. A third option is to leave the solar system after all, not to colonize other stars, which as I've argued is impractical for biological humans, but to build mobile habitats powered by fusion reactors using fuel harvested from Jupiter or other gas giants. Essentially creating artificial wandering worlds that travel through interstellar space, not trying to reach any particular destination, but just migrating away from the dying sun and existing in the void between stars. This is the concept of rogue habitats or interstellar arcs, self-contained civilizations that are no longer dependent on any particular star, but carry their own energy sources. With fusion power and efficient recycling, such habitats could potentially persist for millions or even billions of years, far longer than any star will shine, becoming truly independent of stellar resources. But these are speculations about the very distant future, 5 billion years from now. And it's pointless to try to predict in detail what capabilities or decisions our descendants will have. The more immediate point is that the solar system provides a home for consciousness for timescales that are incomprehensibly long from any human perspective, billions of years. Enough time for evolution to completely transform whatever species we become. Enough time for civilizations to rise and fall thousands of times. Enough time for every possible experiment in how to live and think and organize to be tried exhaustively. So the constraint of being solar system bound is not really a constraint on any meaningful timescale. It's only a constraint on romantic notions of spreading across the galaxy, and abandoning those notions cost us nothing of real value. Now let me address the existential risks that a solar system civilization faces. Because even though we're not facing the immediate threat of the sun dying, we do face nearer-term challenges that could determine whether we survive to build a mature space civilization. The most serious existential risks are technological, arising from our own capabilities and choices rather than from external cosmic threats. Nuclear war could destroy human civilization and make Earth uninhabitable for centuries. Though probably not cause complete extinction, since some people would survive in remote locations or in bunkers. But a nuclear war would certainly set back any plans for space colonization by centuries. We'd be focused on recovering and rebuilding on Earth rather than expanding beyond it. And the political and economic instability that would follow might prevent the coordinated long-term investment needed for space development. Engineered pandemics are potentially more dangerous than nuclear war because biological agents can spread globally and could potentially cause extinction if they are sufficiently lethal and contagious and resistant to treatment. As biotechnology advances, the capability to engineer dangerous pathogens becomes more accessible, and either through accident or deliberate attack or even just reckless experimentation, we could create and release something that kills most or all of humanity. This is a growing risk. As the technology becomes democratized and it's not clear we have adequate safeguards or governance structures to prevent it, we're relying on a combination of technical barriers that are eroding and social norms that might not hold under all circumstances. Artificial intelligence poses existential risk through several pathways. The most discussed being the development of super-intelligent AI that pursues goals misaligned with human survival or flourishing, either because it's programmed incorrectly or because it develops emerging goals that we didn't anticipate. An AI that's smarter than humans and able to act in the world could potentially outcompete us for resources or reshape the environment in ways incompatible with human life or simply eliminate us as threats to its goals. This might sound like science fiction, but it's taken seriously by many researchers in AI safety. And the consensus is that we need to solve the alignment problem. Figuring out how to create AI systems whose goals remain compatible with human values even as they become more capable before we create systems that are capable enough to pose existential risk. Environmental collapse is a slower moving but still serious risk. If we degrade Earth's environment enough through climate change or pollution or resource depletion or ecosystem destruction, we could create conditions where human civilization can't be sustained at its current level or at all. This wouldn't cause immediate extinction, but it could cause societal collapse, mass starvation, resource wars, breakdown of technological infrastructure, and a retreat to much lower population and capability levels. And if that happens before we've established self-sustaining presence beyond Earth, it could prevent us from ever developing space colonization. We'd be trapped in a degraded Earth environment, unable to escape, and eventually we'd go extinct through some combination of further environmental degradation and random catastrophes that we no longer have the resources or knowledge to survive. So the critical period for humanity is the next few centuries. This is when we face the highest concentration of existential risks from our own technology before we've developed the wisdom and governance structures to manage those technologies safely, and also before we've established backup populations of Earth that could survive if something goes catastrophically wrong on our home planet. If we can get through this period without destroying ourselves, if we can manage the transition to advanced technology and begin establishing permanent presence beyond Earth, then our long-term survival becomes much more likely. We become harder to kill, more distributed, more resilient, less vulnerable to single-point failures. But if we fail during this critical period, if we destroy ourselves through nuclear war or pandemics or AI or environmental collapse, then the entire potential future I've been describing disappears. Consciousness in the solar system ends and the universe returns to the dead state it was in before life evolved on Earth. This is why some philosophers argue that reducing existential risk during this critical period is the most important thing we can do. The expected value of the far future. All the trillions of potential people living in space habitats across billions of years is so enormous that even small reductions in extinction probability have astronomical value worth enormous sacrifices in the present. And I think there's something to this argument, though I'm wary of utilitarian reasoning that tries to cash out everything in terms of numbers of future people, because that can lead to neglecting present suffering and justice and rights in favor of abstract calculations about hypothetical futures. But the basic point is sound. We are living in a uniquely dangerous and important time when our actions can determine whether consciousness persists in the solar system or disappears forever. And taking that responsibility seriously means prioritizing long-term survival and the establishment of space-based civilization, even if there are significant short-term costs. So, let me synthesize all of this into a coherent picture of humanity's future. We are confined to the solar system. Interstellar travel is effectively impossible for biological humans and probably not worthwhile even if it were possible, because the costs vastly exceed any benefits. But the solar system is vast, containing enough energy and materials to support a civilization far larger and longer lasting than anything that could exist on Earth alone. Building such a civilization is technically feasible with foreseeable technology, though it requires solving significant challenges in propulsion, life support, radiation protection, resource extraction, and social organization. The timeline is centuries to millennia, not decades. This is a multi-generational project that will unfold slowly and will require sustained commitment and capability across longer periods than human institutions have historically persisted. If we succeed, the result is a decentralized civilization of millions of habitats supporting trillions of people with enormous diversity in social organization and values and pursuits, powered by abundant solar energy existing for billions of years until the sun dies and forces another transition. If we fail, if we destroy ourselves during the current critical period, or if we fail to solve the technical and social challenges of space colonization, then human civilization remains earthbound and vulnerable to extinction from planetary-scale catastrophes or from our own technology. And the long-term survival of consciousness becomes much less certain. So, our choice is not between solar system colonization and interstellar expansion. That's a forced choice because interstellar expansion isn't really possible. The choice is between solar system colonization and eventual extinction. Between building a sustainable multi-world civilization and remaining confined to one planet where we are vulnerable to catastrophe. And framed that way, the answer is obvious. We should be investing heavily in space development and establishing permanent presence beyond Earth and solving the technical challenges of living in space in building the economic and industrial base that makes space colonization self-sustaining rather than dependent on Earth's resources. This is not a luxury or a vanity project. It's essential for long-term survival. And every year we delay is a year we remain vulnerable to existential catastrophe that could end the only known instance of consciousness in the universe. But we also shouldn't be seduced by fantasies of interstellar expansion that distract us from the achievable goal of colonizing our own solar system. We shouldn't waste resources on impossible projects when there's so much to do here that's both necessary and achievable. So that's my message. We're trapped in the solar system by fundamental constraints of physics and biology and economics. Interstellar travel is effectively impossible and pursuing it is a distraction from the real work of building a sustainable civilization within our own stellar neighborhood. But being trapped here is not a limitation or a tragedy. The solar system is home. It's vast and full of potential. It can support everything we might want to achieve as a civilization for billions of years. Our task is to learn to live in it, to expand into it carefully and sustainably, to solve the challenges of space-based existence, to build a multi-world civilization that can persist for geological timescales, and to preserve and spread consciousness throughout our cosmic home. That's an extraordinary goal, one worthy of our greatest efforts and our longest commitments. And achieving it would be one of the most significant accomplishments in the history of life, in the universe. We are trapped here. Yes, but here is enough. Here is more than enough. Here is everything we need for a future beyond our current capacity to imagine. So, let's stop dreaming of impossible journeys to other stars and start building the achievable future that's waiting for us in our own solar system. The only home we'll ever have, the place where consciousness arose and where it can persist for as long as the laws of physics allow. The stars are beautiful. We can admire them from afar. We can send our tiny probes to visit them and send back information. But we are children of the sun. And the sun's family of worlds is where we belong. Where we live and die and build and create an experience for all the billions of years we have remaining. That's not a prison. That's a home. And learning to appreciate it for what it is rather than wishing for what it's not is the beginning of wisdom about humanity's place in the cosmos.